you all for connecting for the lesson. I hope we are all able to hear me. Can I have someone to lead us in out of prayer?
Let us pray. Father, in the mighty name of Jesus Christ, we bless your name, Father, for this afternoon as we're going to start up this lesson. May you guide us, be with us. In the name of Jesus Christ, we are praying. And may all saints
Amen.
say amen.
Thank you, the class. Okay, yeah. So sorry, coming late than I'm supposed to be. But thank you for being patient. Okay. So we'll go straight to where we stopped. That's cool. Okay, so is everyone able to see the document that I'm projecting? Okay, so I know last time you had looked at two experiments, and along the notes I sent the experiment for the dissociation of hydrogen iodide. So for those that went through the notes, you should have seen it, though we hadn't covered it. I just sent you to read through and maybe attempt the question that I sent out there. Maybe someone can respond to me in the chat. Were we all able to get that document and we tried out the activity that I sent? It was just one more. Well, may I get some responses? Was there anyone who attempted? I just want to research. I can know where we can begin from, because I had said those who had attempted would maybe show us how they attempted it. No more. Okay, there seem to be no responses. I don't know if that is a no or my network is just slow because I don't see any response. I see it. Okay, anyways, let's move on. If people attempted the number, they can reply in the chat that they were able to attempt. Anyway, so we have this experiment. We're still looking at how we can find the chemical equilibrium of different substances and how we can obtain those formulas in case we have to get to the high equilibrium state of it. So we had looked at two experiments the previous lesson. And the first one was on the determination of chemical equilibria for hydrolysis of the ethanol using hydrochloric acid and phosphate. Did that, then we also looked at the esterification, which is the other way around. This time we are using the products to get the reactant. So today we'll be looking at the dissociation and the formation of hydrogen chloride. So we have the experiment to determine the equilibrium constant for the dissociation of hydrogen iodide to hydrogen iodine. So of course, like we did last time, you have the procedure, then you have the titration bit, and then you have the treatment of results, which helps us find the formula that we can use to obtain the chemical equilibrium of that given. So our first step here, a known amount of hydrogen iodide, which is N moles, is put in a sealed glass bulb of a fixed volume, and it is kept in a thermostat at a temperature of 550. Because remember, we said the temperature has to be constant, and it has to be in a sealed system so that you're able to regulate the conditions that are taking place. So until equilibrium is established. So at equilibrium, the bulb is removed and rapidly cooled to stop the reaction and fix the equilibrium such that the equilibrium doesn't adjust itself to the equilibrium value at a low temperature. Then the tube is then broken under an aqueous solution of potassium iodide to dissolve the iodine present at equilibrium. Sorry. And then the resultant mixture is titrated with a standard solution of sodium thiosulfate using starch indicator. So in this case, we have the titration equation, which involves iodine and the thiosulfate to give you iodide ions and the sulfate ion. So the amount of iodine at equilibrium is obtained. So we are going to consider our total volume as V, and then the number of moles of iodide heated. Those are the C moles. Remember the initial number of moles of hydrogen iodide were N moles. So at this point, the moles that are heated are C, and then the degree of dissociation of hydrogen iodide is alpha. Because remember, we are dissociating the hydrogen iodide to give us its consistent components, which is hydrogen and then the iodide gas. Sorry, the iodine gas. So that means we need the degree at which the hydrogen iodide dissociated, and in that case, it's the alpha. Okay, so at this point, we have Maggie, is it your first time here? This is chemical equilibrium. We started on it last week. So we have the initial moles which were given to us because remember we said when we are working with the chemical equilibrium, we start from known to get the unknown. So in this case, the initial moles are the N moles. And then because we are just starting the experiment, like we said last time, that means the products have 0 moles at their initial stage. So that means we have 0 for hydrogen and 0 for the iodine gas. And then because there is a degree of dissociation, so that means we multiply the initial moles times the degree of dissociation because that is the rate at which that component dissociated to give you its appropriate compounds. So at that point, that means we have the N alpha. And since we have N alpha, remember here we have 2 moles because of the, to balance the equation, you realize that we have a 2 here and a 2 there. Since this side we have only 1 of each of them, so that means to balance the equation, we'll have a 2 on the hydrogen iodide. So in that case, that means for us to get the number of moles that were formed, we need to divide by 2. That is why you have N alpha divided by 2 and then N alpha divided by 2. So that means if 2 moles dissociated this side, that means this side, each one comprises of half of that contribution. That is why you have N alpha divided by 2 and then alpha divided by 2. And then remember we said when we are getting the moles at equilibrium, we get the initial moles minus the moles that were formed or the moles that dissociated. So that is why you come to the next stage and you have N minus N alpha. And then here, since we had 0 moles as the initial moles, that means they retain their moles as N alpha divided by 2 and then alpha divided by 2. Then the concentration at equilibrium, remember, we also said we need to consider the volumes at which those different experiments occurred. And in our treatment of results, our volume was V. So that is why we get the number of moles at equilibrium divided by the volume, because that is what gives us the concentration. You get moles divided by the volume. So in this case, because N is common for both of them, that means we'll have N into N, N, so we have N alpha, but N is common here and here, so that means we pull out the N and remain with N. Here we remain with 1 minus the what? Minus the alpha. So that is what we have here. N into 1 minus alpha N over V. And then this side, since we already had a 2, you just divide by V side as well. So after that, remember we said for us to get KC is obtained by getting the concentration of the products to their powers, to their appropriate powers, maybe X, over the concentration of the reactant to their constituent power. So that is what is happening here. We have the products, which is hydrogen and then iodine. We multiply their concentrations over the concentration of the reactants. So in that case, since we have N alpha 2, then N alpha 2, and both of them are to the power 1, that is why you realize that here we have N alpha over 2 times N alpha over 2. So because they are happening twice, that is why we have a power 2 here. And then because we have a 2 in front of the hydrogen iodide, that is why we power the concentration at equilibrium by 2, because remember we said we raise them to their appropriate powers. And then in that case, we'll have in that case, we are going to have N over 2V squared divided by N into 1 minus alpha over V squared as well. So here, since we have this, that means we are going to have N alpha squared over 2, which is 4V squared. Because 2 times 2 still gives us 4. So times, you will have, since I've changed the sign from division to multiplication, that means I'll have V squared divided by N squared into 1 minus alpha squared. So this N squared will cancel. This will cancel with that. And then the V will cancel with this V here. So that means I'll remain with my Kc as equal to alpha squared divided by 4 into 1 minus alpha squared. You can choose to expand this bracket as well, it still gives you the same thing. So that is how basically they came up with this Kc for the dissociation of hydrogen iodide. Are we together up to that point? Am I saying pardon on that part? Which part exactly?
Excuse me, madam, what is N and alpha representing?
Oh, did you just log in?
Yeah.
Okay, so what is happening here? We said that N, let me just scroll back up there a little bit. now when you're looking at the experiment, we said when you're looking at the at this experiment of equilibria, we start from known to unknown. So in case you're carrying out any experiment, of course you'll have something that you know. So in this case, since we are dissociating hydrogen iodide, that means we started with the N moles. So unknown amount of hydrogen iodide, which are the N moles, is put in a sealed tube. So the N came from the initial number of moles of hydrogen iodide, like you can see here. Kabakos, are we together? Sorry, Kabos. Emma.
Yeah, we are together, madam.
Okay, so at that point, we say that the N moles are the ones that we start with the initial moles. And remember, at the starting point, because we are dissociating hydrogen iodide, that means we do not know how many moles are in hydrogen and then what? Iodine. That is why for them, the initial moles are what? 0 and then 0, while the one for hydrogen iodide is what? Is N. And then, of course, when we go into the treatment of results, we have our total volume as V, and then the number of moles of hydrogen iodide that were heated was C, and then the degree of dissociation of hydrogen iodide. Because remember, we are breaking hydrogen iodide into its constituent components. So in this case, that means there is a degree at which it dissociates at equilibrium. So that means we cannot ignore that degree of dissociation. That's why we let it to be alpha. So the moles that were dissociated, that means they became N alpha. And because this side, we have hydrogen as 1 mole and iodide as 1 mole, to balance the equation, this side we have what? 2 moles of hydrogen iodide, dissociating to give us 1 mole of hydrogen and 1 mole of iodine. So in that case, that is why we get the N alpha as the number of moles that dissociated. But for us to get the components, the moles that were formed, we get the N alpha divided by 2 and then N alpha divided by 2. Emma, are we together up to that point?
Yes, madam.
Okay, Midline, you're saying my voice is low, but I feel like I'm screaming. I don't know if you can increase your volume a bit, or it's true for everyone that my voice is actually low. So, and that's where we came in and said the number of moles at equilibrium, if you're getting the number of moles at equilibrium, we said you get the initial moles minus the moles that dissociate. So in that case, we'll have N minus N alpha. And then here, since they are 0 and 0, that means we consider the moles that dissociated as their moles at equilibrium. That is why you will have,
Excuse me, madam.
yes, please.
Why do we multiply the initial moles by the degree of dissociation?
Oh, that's a very good question. So we are multiplying them because we need to know the moles that happened at equilibrium. But remember, at equilibrium, we are dealing with a component that dissociated into its constituent what? Its constituent elements. So we need to know how much of those elements came from the original composition of that compound. I don't know if that answers your question.
Oh, yeah. It's okay.
Yeah, so we need to know how much was produced from the origin. Because in this case, we are not dealing with two compounds giving us something else. We are dealing with breaking a compound into its constituent what? Elements. So in that case, we need to know at what degree did that happen. That is why we multiply it.
Okay,
So can we
madam.
continue?
Yes.
Okay, so after that, after subtracting, of course, we say to get the concentration, you get the number of moles over the what? Over the volume. That is why we have, here we just got N as a common factor into 1 minus alpha. because when you multiply, it still takes you back to this when you open the brackets. So that will be the concentration at equilibrium for hydrogen iodide, and then divide by the volume, divide by the volume, which still gives you the same for hydrogen and iodide. Then you're going to getting the chemical equilibrium. We said if you're representing it as concentrations, we use case C. So in that case, we are using the concentration of the products over the concentration of the reactants. So you will get the concentration of the hydrogen and then the concentration of iodine. That is why we have N alpha over 2V squared. So
Excuse me,
am I clear?
madam. Excuse me, madam.
Yes?
When we are dividing with the volumes, do we use the initial volume for the hydrogen iodide for all the components?
Yes, because remember, we are looking at the total volume in the tube, in the bulb. And we expect that if they have reached equilibrium, their volumes are more like the same. Because remember, we are looking at only reversible reactions when we are looking at chemical equilibrium. That means the same volume that was broken into hydrogen and iodide is the same volume that will give us the hydrogen iodide. So that is why we consider the volume to be constant for all of them.
Okay,
Have I
madam.
answered your question?
Yes.
Okay. So, Emma, were you following on the remaining part so that we move on, or you need me to redo the calculation?
The calculations.
Sorry?
It was the calculation that were disturbing.
Oh, okay.
Madam,
So
madam,
I said
please.
when we have KC, KC will be the concentration of the products over the concentration of the reactant. So in this case, our reactant is hydrogen iodide. And we say that when we are finding KC, we get the concentrations and raise them to their appropriate powers. So for hydrogen, you realize that the power here is 1 and here is 1. So that means they were raised to 1. But like you do in math, we can't write 1x. You write x as it is to represent 1x. So it's the same thing happening here. You have the concentration of hydrogen and the concentration of iodine. Then for hydrogen iodide, because it has a 2, that means we raise it to its appropriate power, which is a what? Which is a 2. So in that case, we come and look at their concentrations at equilibrium. Yes, Nancy, your hand is up.
Yes, madam, my question is, those appropriate powers, are they stoichiometric values? Or
Yes, the values from the stoichiometric equation.
okay, madam.
Okay, so after that, we know that the concentration for hydrogen is N alpha divided by 2V. And then the concentration for iodine is still the same thing, N alpha divided by 2V divided by the concentration of hydrogen iodide, which is this one here, N into 1 minus alpha over V. But because its appropriate power is 2, that means the whole thing is squared. And because there is a repetition here, we are multiplying the same kind of bracket. That is why we have a squared here as N alpha over 2V squared divided by N into 1 minus alpha over V squared. So in this case, I'm going to open the brackets and I'll say N squared alpha squared over 4V squared times, and since I am changing the multiplication sign, Since I'm changing the division sign into multiplication, that means I get the reciprocal of this. But still, I'm also going to open the brackets for this. So that means I'll have v squared divided by n squared into 1 minus alpha squared. So because n squared is appearing here, I can cancel here and cancel that one, that side. And then v squared is also appearing here, I can cancel those two. So that means I'll have alpha squared over 4 into 1 minus alpha squared. So that will be our case C for the dissociation of hydrogen iodide as per that experiment. Yes, take me.
Excuse me, madam, sorry for disturbing, but at this point of moles dissociated all formed, why do we divide by 2? Can we just multiply the moles formed by hydrogen iodide by 2, then the rest we just leave them as they are?
Will it still give you the same case C if you tried it out?
Let me try it out and see.
Yeah, you try it out and give us feedback. Okay,
Okay,
so
madam.
because it's supposed to give you the
Excuse me,
same
madam.
exact case C. And okay, so Emma, did you understand up to that point? And the rest of us that joined later on.
Yes, madam.
Okay. I'm checking on you get that final answer. Okay, so if there are no questions, we can move. So like we did for the esterification and then the hydrolysis of the ethanol, it's the same thing we are going to do here. Since we looked at the dissociation of hydrogen iodide, now we are going to look at the formation of hydrogen iodide. So in this case, we have a known amount of hydrogen, which is A moles, and then a known amount of iodine, because remember this time round, we have two components giving us one component. So we have hydrogen and then iodine giving us hydrogen iodide. So that means we need to know the amount of hydrogen and then the amount of iodine. So in this case, we have a known amount of hydrogen, which is mol. Like we did last time, you can keep noting down this value so that when we get to the formula, you're not lost of where we got what later. So in this case, we have, I'll put in a sealed glass bulb of a fixed volume, which is V, kept in a thermostat at a temperature of 450 degrees until equilibrium is established. Okay, Jege, I don't know if that's the right pronunciation. Your hand is up. Okay. So we have at a temperature of 450 degrees until equilibrium is established. So at equilibrium, the bulb is removed and rapidly cooled to stop the reaction. And the fixed equilibrium, and you need to fix the equilibrium such that the equilibrium does not adjust itself to the equilibrium value at a lower temperature. Then the tube is broken under an aqueous solution of potassium iodide to dissolve the iodine present at equilibrium. So the resultant mixture is titrated with a standard solution of sodium thiosulfate using a starch indicator. And then that is the equation for the reaction of titration. And then the amount of iodine present at equilibrium is obtained. So in this case, we have our total volume as V, and then we have the number of moles of iodine converted to iodide are X moles. Third means the moles of hydrogen iodide formed are 2X. So that is important to take note of some of those things. Then here we have the treatment of our results. We have the number of moles. Remember, initially we said for hydrogen, we have A moles. And then for iodine, we have B moles. And then because we are forming hydrogen iodide, it has 0 moles at its initial start, at the initial stages, sorry. So the number of moles that reacted were X moles, like they have told us in the experiment. So because remember, we are supposed to obtain this number of moles from our titration experiment. So that means if they have told us, let the number of moles of iodine that were converted to hydrogen iodide be X. If the number of moles that produced hydrogen iodide are X, that means even the number of moles of hydrogen that reacted were what? Were X. So at that point, even the production of hydrogen iodide, because we are producing 2 moles of hydrogen iodide, that means it becomes 2 times what? Times X for the number of moles that were produced. So at that point, we have the moles at equilibrium. The number of moles at equilibrium, we said we get the initial moles minus the what? The moles that were formed or the moles that reacted. So in this case, we'll have A minus X, and then for iodine, we'll have B minus X, and then for hydrogen iodide, we'll have it as 2X. Then in this case, the concentration at equilibrium, we said we get the number of moles at equilibrium divided by the volume, by the total volume. So that means we'll have A minus X over V, and then here we'll have B minus X over V, and then we'll have 2X over V. And like we said, when we are dealing with case 6, we have the products, the concentration of the products raised to their powers, to their appropriate power over the concentration of the reactants raised to the appropriate what? Powers. So that means our product this time round is hydrogen iodide. And you realize that the number of moles are 2, so that the power reached were 2. And then for hydrogen iodide, sorry, for hydrogen and then iodine are the reactants this time round. So that means we are going to have our case C is equal to the number of moles, which is 2X over V squared divided by what we have here, A minus AX over V into B minus X over V. So this is one bracket that is being divided by the rest. There's something for requesting to record locally. It's really important because you'll have to what? The video will still be posted. So we have 2X squared over V squared. Sorry, this becomes 4. Since it is squared, so it becomes 4 divided by, so this one will have A minus X into B minus X over B times B gives us B squared. So that means I'll have 4X squared divided by V squared times B squared divided by A minus X into B minus X. So because V squared appears on both, I'll have this V squared go with that V squared. And this will give me my Kc as equal to 4x squared divided by a minus x into b minus x. And that will be our Kc for the formation of hydrogen iodide from hydrogen and iodine gas. Okay, are we all together up to that point?
Yes, teacher.
Okay, thank you. Taking note, have you got the solution to the task that we had?
Yes, madam, it was the same.
So that means it's still okay to, because the other side we are dividing by chosen being the number of moles of hydrogen iodide were twice what was produced on the other side. So that is why we were basically dividing. I wanted you to discover that you still get the same thing. Okay, so can now move on to the next. So remember, in our introductory part, we said we can calculate Kc in two ways. We can calculate Kc in terms of molar concentration, and we can also calculate Kc in terms of pressures of those different equilibria. So in this case, we have this question here. So who still remembers the equation we got for equilibria of the esterification of the ethanol? Because I want us to do this calculation together. Okay, so let's just have someone read for us the question. Anyone to read for us the question? Yes, Dr. Pretty.
The question says, when 60 grams of ethanoic acid were heated with 46 grams of ethanol until equilibrium was established, 12 grams of water and 58.7 grams of ethanoate were formed. Calculate part A, the equilibrium constant for the reaction. Part B, the mass of the ethyl ethanoate that would be formed under the same conditions if 90 grams of ethanoic acid and 92 grams of ethanol were heated.
Okay, thank you. So in this case, we are basically going to apply the knowledge we've learned. Remember, if we have the masses, we can actually find the number of moles that are constituted in each of those compounds that have been given to us. So the question is telling us we have 60 of ethanoate, of ethanoic acid, and then we have 46 of ethanol at equilibrium. So in this case, we have until equilibrium is established. So that means these are our reactants. This is a reactant, and this is a reactant. I've seen someone write for us the equation in the chart. That is very good. And then we are forming 12 grams of water and 58 grams of the ethanol. And these are our products, the water and then the ethanol. So they're telling us to calculate the equilibrium constant. So they are telling us in this case to find Kc, because we can easily get the concentrations by knowing the molar masses of these different of these different substances. So in that case, here we have the molar mass. Of course, you can go ahead and calculate in it as well. The molar mass of ethanoic acid, we have 2 carbon atoms. That is why you have 2 times 12. And then you have 2 moles of oxygen. So you have 2 times 16 plus. Then you have 4 hydrogens, 4 times 1, which is equal to 60. You can confirm the calculations if the values are actually the ones that I've given us here. And then the molar mass, we have 2 carbon, the molar mass of the ethanol, we have 2 carbons. That means we have 2 times 12 plus we have, this is supposed to be 6 times 1 because you have 6 hydrogen and then you have 1 times 16, which are the oxygens to give you 46 grams. Do we all concur with those molar masses? Okay, so if the molar masses are those, and then they gave us the initial masses. So to get the number of moles of ethanoic acid and ethanol weight, we get the number of moles of the molar concentration divided by the number of moles that reacted. So that means in that case we have, since we have 60, so that means we'll have 60 divided by 60 to give us 1 mole. And then we have 46 of ethanol, so we get the molar mass divided by the moles that reacted, which is 1.0 moles. Then the molar mass of water is obviously 18. And then the molar mass of the ester, which is 4 times 12 because there are 4 carbons, then 8 times 1 because of the 8 hydrogens, then 2 times 16, the 2 oxygens, which gives us 88 grams. So the number of moles of water at equilibrium, remember that when equilibrium was established, 12 grams of water were produced and 58.7 grams of the ethanol weight. So that means in this case, we get the number of moles that were produced over the molar mass. So that we get the moles that were produced at equilibrium for both of them. Are we together up to that point? Okay, thank you. So we have, of course, you have to write the equation. Like I said, someone already posted in the chat what the equation was. So that means in that case, we are going to have the initial number of moles. Remember, our initial number of moles are the moles that we obtained as a result of the reaction taking place. So we have 1.0 and then 1.0. So that means our initial moles are 1.0, 1.0, and yet for the products being formed, they are still at 0 number of moles. Then the moles that reacted, because remember we are dealing with equilibrium, all of them have a molar concentration of the mole ratio. When you look at the mole ratio, it is 1 to 1. So that means the number of moles that were produced, that reacted or were formed are the same. That is why you realize that we are taking the number of moles of the ester and the number of moles of water to be the number of moles of the ethanol and then the ethanoic acid. So that is why you see that for this whole line, we have 0 0.67, 0 0.67, 0 0.67. Yes, take note. Tekno, your hand is up. Okay, maybe as you unmute, someone has a question. Why do we consider the water yet the other time we said we shouldn't include it? I remember I emphasized that point. Can someone remind us if you remember what I said? Because we emphasized and I actually told you to write it down as it was. We even take a screenshot. Anyone who remembers why we said we consider water in this state? candidates. We need to remember these concepts. Eh? So, yes, Rashida.
Okay, madam, you said that if water is one of the reactants and its concentration is given, you have to consider it.
Okay, very good. So we say if water is one of the reactants, thank you so much, Rashida. If water is one of the reactants, in that case, we say we consider it as a product. Sorry, if water is one of the reactants and it's in liquid state, we consider it to be, we consider that that reaction took place in an environment where the water was in excess. So that means we do not look at the water. But if water is given off as a product, we consider the water. And if water exists in gaseous state, we'll still consider it if it's on the reactant side or on the product side. So the only instance where we don't consider water is if water was the necessary reactant required for that reaction to take place. So if it is required for that reaction to take place as a dissolution agent, sorry, as a dilution agent, that means we don't consider it to have a what? A molar concentration. But in this case, we really can consider it to be one. Okay, so have I answered your question, the person that asked in the chat? And Rashida also tried to comment. So that goes.
Excuse me, madam.
Okay, thank you. So in this, sorry?
Excuse me, madam.
Yes, please.
What if in the calculation we get the moles of water different from the moles of the ethyl ethanoate?
Of course, now that will happen depending on the molar concentration you have in the stoichiometric equation. Because if we have the number of moles being 1, then we expect at least there should be a uniform kind of distribution between those number of what? Of moles. I don't know if I've answered your question.
Yes, but for the case when they are different, what do we have to do?
Of course, now after understanding this one here, it will become easy because like we found out on hydrogen iodide, where you have to divide the number of moles. Like the same way you can have 1 mole reacted to give you 2 moles. So if I have 0.067 moles this side, what is going to be my molar composition this side?
0.067 times 2.
Sorry?
0.067 times 2.
Times 2. So it's the same application that you will need to apply when you have such instances. So you compare the mole ratio. The mole ratio is what sends you on what you're expected to do per moles that reacted and per moles that were formed. Is that clear?
Yes, madam.
Okay. So so in this case, we have the number of moles being the same. So we say to get the moles at equilibrium, we subtract the initial moles minus the moles that were formed or the moles that reacted. So that is why we have 1 minus the moles at equilibrium and then 1 minus the moles that reacted. Then of course we have the other ones remaining constant as they were because of the zeros that are happening there. So in that case, we go to finding our chemical equilibria. And in that case, we say chemical equilibria is equal to the concentration of the products divided by the concentration of the reactants. That is why we have the ethanol weight and then the water. Sorry, the ester and then the water, and then we have the ethanoic acid and then the alcohol. So here we have our concentration as so our concentration here is going to be the number of moles produced at equilibrium divided by the number of moles that were produced at equilibrium for both instances. So if we have the one for the ethanol weight, and the one for the ester, the one for water, which is this and that, and then you have them squared here because they are similar, so they are squared. Then this and this, they are okay, Hannah, can you share with me the first right? Sorry, I had gone over. You can just click on my name and then co-host me.
Teacher, I'm done. You're the host now.
Okay, can you hear me?
Yes, teacher.
Yes.
Sorry
Yes.
about that interruption. Okay, so Part B is telling us to calculate the mass of the ethanol wet that would be formed under the same conditions if 90 grams of ethanoic acid and 92 grams of ethanol were heated. So who can take us through that part? Who can tell us what we are expected to do? Anyone with an idea? So in this case, we have in this case, they told us the number of moles, if the number of moles of the ethanoic acid that were heated were 90. That means in this case, we are going to have the number of moles were 90, and then we got the RMM as 60. So when you divide 90 by 60, it gives you 1.0. And then the RMM for the ethanol was 46. That means you're going to have 92 divided by the 2.0 moles. So if we have 2.0 moles, we have our reaction. Of course, the equation remains the same because we are still using the ethanoic acid plus the ethanol to give us the ester and then the water. So in this case, the number of moles that were initial for the ethanol weight, for the ethanoic acid were 1.5, and then for the ethanol 2.0, and then initially those for the products are 0.0. And then the number of moles that reacted. At this point, we do not know the number of moles that reacted with these different molar masses. So that is why we did as what? As X, because we do not know what value reacted. So when you let the number of moles be X, since the mole ratio is 1 to 1, 1 to 1 to 1 to 1, that means if this one is X, if X number reacted with X number of moles of the ethanol, that means you are going to produce X moles and X moles of water this side. So someone is asking for help. Where is the problem? Emma? Emma, what's the problem? Okay, I don't know. Maybe you will respond. When you do, we'll see how to help. So when we get to the moles at equilibrium, we said we get the initial number of moles minus the moles that reacted. So that is why we have 1.5 minus X, and then 2.0 minus X, and then X, and then X here, because for them, their initial number of moles was zeros. Then when we are getting case C, of course, that one we've oversunk, we get the concentration of the products over the concentration of the reactants. So the concentration of the products, we have X here and X here. That means we'll have X squared. And then, of course, the concentrations of this and that are 5.0 minus X times 2.0 minus X. But remember, in part A, we got our case C. So it can help us to get the values of what? Of X at whichever side. So in this case, we'll have this bracket, you'll open it and you'll have so at this point, we'll have 1.5x minus x into 2.0 minus x. So when we open the brackets, we'll have 1.5 into 2.0 minus x into 2.0 minus x. So what is 1.5 times 2? Anyone to respond to that? I expect that each one of us at least has a calculator. 3, very good. 3 minus 1.5x minus 2.0x plus x squared. I'm dealing with this lower bracket here. I'm trying to expand it. So what is negative 1.5x minus 2.0x?
Negative 3.5.
Negative 3.5x, very good, plus x squared. So since this one is giving us this lower bracket here, that means you're going to cross multiply. And when you do, that means we'll have our x squared is equal to 4.01 into 3 minus 3.5x plus x squared. So this is going to give us x squared is equal to, what is 4.01 times 3?
12.03.
12.03. Good. Minus, what is 4.01 times 3.5?
14.035.
14.035.
Sorry?
14.035.
14.035 x.
Excuse me, madam.
Yes, please.
Excuse me, madam.
Hmm?
You
I'm saying, excuse me, I can't hear you. So is it Emma? Is it taking? Who is asking the question? Because I can't hear anything. Okay, I think I'm going to continue because I'm not hearing anything. Okay, so plus, here we have 4.01 x squared. So in this case, let's have x squared on both sides. Of course, we are going to bring the x squared this side. So that means we'll have 4.01 x squared minus x squared. I took the x squared this side, minus 14.035x plus 12.03 is equal to 0. Are we together up to that point?
Yes, madam.
Okay, so here what do we get when we subtract 4.01 x squared minus x squared?
We get 3.01.
3.01, good. So we have 3.01 x squared minus 14.035 x squared, x plus 12.03. And this is a quadratic equation. I expect every one of us to know how to solve a quadratic equation. So you will get the values of x. So what are the values of x that we get? Who can quickly feed that into the calculator and tell us the values of x that we get?
The first one is 3.530.
3.53.
And 1.132.
1.132.
32.
32. Okay, we can take to 2 decimal place since we've been looking at 1 decimal place. So we can round off to 2 decimal places. Okay, so in this case, we need to choose one of the number of moles that is expected to take on the value of what? Of x. And in this case, we choose the smaller one because you realize that we cannot choose the value of x to be greater than the number of moles that we had initially. Because remember, the value of x is representing the number of moles that reacted or the number of moles that were formed. But those moles can't exceed the initial number of moles that we had. So that means we discard this one and remain with the one that is less than the number of moles we had initially. Are we together up to that point?
Yes.
Madam.
Yes, madam.
Thank you. Okay, so we are going to move to the next example. The next example, we are going to kindly first try out in our books. I hope at least every one of us has our writing material, and then we are going to share our answers, what we have got. So I hope at least we are noting down the questions such that even when we scroll down, we are able to maintain the number of moles. So initially the question asked us the mass at equilibrium. So that means we need to get the RFM of the S star times the number of moles to give us the what? The mass at equilibrium. That is why we have 88 times the 1.4 to give us the 100.32 grams that were required of us. So we have this number 2 here. Let us first try it out before we can do it together. How many minutes should I give us to try it out?
3 minutes.
3 are enough. Okay. Me, I'm timing you here.
5 minutes.
So I'm giving us 5 minutes. That means at 16 minutes past 4, we should be through. And please, if you're through, you can post your answer in the chat.
All right, madam.
Anyone that has obtained the answers? Okay. Rashida, thank you. Then she got 4.08. Okay, so since I've gotten a list of things we can move, the rest can take it with us. So in this question, there is something unique about it. You notice that initially we have both the products and the reactants having the number of moles. So we have the ethanol has 0.051, and then we have 0.0525 number of moles. And then we also have the ester having its number of moles, and then we also have the water. Then we also have the ones for the hydrochloric acid. And then at equilibrium, we have the number of moles of ethanoic acid. So the first thing that you need to do is to write the equation and find out how you're going to distribute the number of moles that reacted, the moles at equilibrium, and then the concentration at equilibrium. Okay, there is another answer from Ibra. Okay, those are good people who tried out. I hope the rest of us are still trying out though. Okay, so here we have the number of moles that it had initially. And then of course they gave us the number of moles of ethanoic acid, which is 0.025. So that means since all these have different number of moles, we are going to subtract by those number of moles. Because remember we said if the mole ratio is 1 to 1 to 1, to get the moles that reacted, we need to subtract the moles at equilibrium minus the moles we had initially. So that means in this case, you'll have the number of moles that reacted, which is 0.27, which occurs for the rest because of the 1-to-1 mole ratio. And then here we have the moles at equilibrium. We have the number of moles that the initial number of moles minus the moles that reacted. And then still the same thing is applying on the ethanol. We have the number of moles that were initial and then the number of moles that reacted. Then when it comes to the number of moles at equilibrium, we get the initial number of moles plus the moles at equilibrium. The initial number of moles and the moles that were formed for you to get the moles at equilibrium. Because remember, we need to know how many moles were formed plus the initial number of moles to know the number of moles that were there by the time the experiment reached what? Equilibrium. The same thing is happening for the water. We get the initial number of moles plus the what? Plus the number of moles formed. Then of course the Kc is simple for us by now. Then the Kc in that case is that. And then for some people that are rounding off to give us 4.10. But it would be better to at least leave it to 2 decimal places, especially if you've been operating in 3 to 4 decimal places. So it's better to at least round off to 2 decimal places than rounding off to 1 to keep the level of accuracy higher. It's better you round off to 2. So I've seen some answers here. Leah is asking 0.22. I don't understand your question. This one is supposed to be 0.7, 0.027. The 7 was left out, but it's supposed to be there. So basically, that is what you have for that. Thank you all for trying out. That was good. Yes, basically that is what happens. That explains why the other side were having the number of moles maintained, because when you add them to 0, it would still give you a 0. Oh, okay, Leah. That's good. Okay, are the rest of us together with us, even those who haven't posted their answers in the chat? Are we all together?
Yes, teacher.
Yes, madam.
Okay, thank you. Your feedback is always important. It helps me know whether we should move or we stay at that point. Okay, there is another question here. We are still going to try it out and then we can harmonize together. So we can copy it down. This one here. So how many minutes should I give us for this one here? Still 5? Should I still give us 5 minutes for this one here? Okay, someone responded. Holly, thank you. And then I can leave us a question to try out by the time at least it shuts down. It's warning me. So I don't want me to just find myself already out of class before I conclude. So let's just do this number together. And if you have found the answer already, you can post it in the chat. There is no harm in that. So if I go off by any chance, the person who will be recording, you will stop the recording so that at least we can have the video at the end of the lesson. So here they told us 1 mole of ethanoic acid was mixed with 5 moles of ethanol. So that means these are the moles that they began with the initial number of moles. And then in a sealed glass tube, and then the tube was pulled in a solution of this. So that means for us to get the concentration or the number of moles that reacted, we need to know the number of moles that reacted for sodium hydroxide. That means we'll get 1,000 contain 0.2. So we'll have 1,000 centimeters cubed of sodium hydroxide contain 0.2 moles. How about 289 centimeters cubed? How many moles will they produce? That means I'll have 0.2 times 289 out of what? Out of 1,000. So that gives me the number of moles of what? Of sodium hydroxide. So when I write the equation between the ethanoic acid and the sodium hydroxide, that will give me the sodium ethanoate plus water, and you realize that it's a ratio of 1 to 1. So if the ratio is 1 to 1, that means the number of moles of sodium hydroxide are the same number of moles as ethanoic acid. So in that case, you'll establish the number of moles that were present at equilibrium. Then of course, you'll write the equation for the reaction between ethanoic acid and then ethanol, which will give you the ester and then the water. So in that case, since we have the initial number of moles, that's what you'll begin with, which is 1 mole and then 5 moles this side. And since we don't know the number of moles the products had, we put them as 0. And then the number of moles that were formed, remember we put the number of moles that reacted after getting the number of moles of ethanoic acid that reacted with sodium hydroxide. So you'll get the initial number of moles of the ethanoic acid minus the moles that were produced at the reaction. And then you'll have 0.942. That will occur for the rest. Because remember, we said if the ratio is 1 to 1, that means the number of moles remain consistent for the rest of the products involved in the reaction. So at that point, we'll get the moles at equilibrium. And the moles at equilibrium, in this case, we have the moles at equilibrium, we have 0.057, because those were given to us with the question. Then of course, to get the number of moles of equilibrium of ethanol, we get the number of moles initially minus the number of moles that reacted. Then for the number of moles at equilibrium for the ester and the water, you get the number of moles that were formed plus the initial moles, the number of moles that were formed plus the initial moles to give you this and that. And then of course, you'll find your Kc by getting the concentration of the products over the concentration of the reactants to give you that Kc as 3.79. Is there anyone who had gotten that answer?
Yes, madam.
No.
Okay, that is good. So basically, that is how you calculate cases. You just look at the question they have given you, find out what have they given me, what do I need to find, and then you keep correlating the required information accordingly. Okay, hopefully we got that and we are together at that point. So I'm going to share with us a number here. Of course, I'll share some more numbers with Mr. Kaziba to share them with us. But I want you to copy down this number such that in case I go off, you can try it out as you wait for the rest of the numbers.
You see this is number doing. So he has opened up now.
Okay, so we have one of hydrogen iodide here.
They are trying to do about chemical equilibrium. Equilibrium is involved in hydrogen iodide and
Saying
hydrogen.
something.
All dissociation will be treated in terms of degree of dissociation, and punctuation. The degree of dissociation is the fraction or percentage of the undissociated molecules which have dissociated. Here the unit class
Okay, so maybe something I need to emphasize. When you're looking at hydrogen iodide, remember we said hydrogen iodide splitting into its constituent elements, which is iodine and hydrogen gas, requires dissociation. So that means there must be a degree of dissociation occurring. So that means for any of other compounds that we'll look at that involve dissociation, you'll have to introduce the degree of dissociation like we saw in the experiment. So that is what you're going to do for the case here as well for this point, where we have the equilibrium constant, because you're splitting the hydrogen iodide into its constituent ions. So you can try that number. Ambrose, you're welcome. And thank you for attending. Okay, technically asking when do we apply degree of dissociation? I'd say
Guys, has Madam gone off?
I think she's off. Has anyone?
She has gone off, eh?
Yes.
Okay, now who is the host? I think Hannah is the host.
By members for the lesson.
Should I end it? Because I don't know how I'm the host now. Should I end that?
No way to end it. Please help me with a question.
You pass away. Okay, you give me the rights.
Let me see, what's your name?
You tap my name, Ambrose.
Okay.
Tap on my name, then you give me the rights. Okay, thank you.
Ambrose.
Yes, please.
Help me with a question.
Let me try to get it.
I need questions too. This is Zabra. This is Zabra and questions too.
I beg your pardon.
Jose.
This Abra, I need your question too. I need a question.
Okay.
The question is?
Yes.
3 moles of hydrogen. Is everyone listening?
Yes.
Yes, we are getting you.
3 moles of hydrogen and 1 mole of iodine
Yes.
were heated together in a sealed tube at 500 degrees Celsius.
Okay, okay, let me see. Yes, you move on.
Until equilibrium was established. Calculate the number of moles of hydrogen iodide.
Calculate the number of moles of hydrogen iodide. Yes.
Present in the equilibrium at 500 degrees Celsius.
Yes.
And in brackets, the equilibrium constant for the reaction between hydrogen and iodine is 50.
Yes.
Part B, describe briefly how the concentration of iodine equilibrium can be established or obtained.
Yes. Okay, Lena is like she wants to share her screen.
Wait.
Please share your screen. Bro, meanwhile you can continue.
That was the question.
Okay. In case maybe someone has not picked it properly, the recordings are going to be there in the group. So you can still get it from there. But also I'm seeing Lena is sharing her screen for someone who wants to take a screenshot. Share your screen. Okay. Try to zoom it. Okay, someone can take a screenshot, then maybe you now get a question direct.
Please.
Or else you can even still get it in a recording. Just follow from the recording because it will be posted there in the group. When there is someone here asking about what.
But some of us are not in the group.
You are not in the group?
Yes.
Can I post the link for the group?
No, when we try to enter, they are telling us that the group is full.
Auntie, I can still get another link. There is a group which is full. That one of senior 6A is full.
Okay, you can get us another one.
Okay, let me see. I think someone has even posted it.
But I'm not seeing it.
Yeah, you can now remove the screen. You You can unshare your screen. We have finished. Yes. Okay. Okay, Juliet, I'm going to share it. But let me first try to get it. I don't know which one is which. Let's be waiting. Let's be waiting. I'm getting it. I'm getting it. Nah, you go out. Okay. Let me now post it.
What's going on?
I'm posting it. So I hope you guys can see the link now. Okay, guys, bye. Let me end the meeting. Unless if there's someone who wants to say something before we go off, because we need to. Yes, please.
Please don't forget to send me the link on my number because right now I'm using a PC and it has no WhatsApp.
It's okay, I'll send it. I think I've got your number.
Thank you.
You're welcome. Okay, I think I can end it. So bye, guys.